All right, ladies and gentlemen, it's a pleasure to be here today. My name is Navid Jafari. I am presenting a presentation on highway slope stability and embankments. My collaborator, co-PI, is Anand Bhupala, who's sitting over to the left. Barack Bullock, who is a graduate student working on the project, is sitting in attendance as well. Tejo Bihimaseti, unfortunately, could not make it to the conference. And Jack Cadigan is also here working from LSU as a graduate student. So the work that I'm presenting today stems from discussions on the local level from DOT on what is some of their concerns with geotechnical infrastructure. And one of those big ones that they came back to us was performance rehabilitation of highway embankments. So this presentation will go over some introduction to highway embankment slope stability, give updates on the project, and look at what we're doing right now, whether with regards to stability analyses, unsaturated modeling, and material properties, and also looking into some of the higher end or more refined climate modeling. And we'll finish with conclusions. So highway embankment slope stability, shallow slides, has been an ongoing problem ever since construction of these embankments 30 to 40 years ago. There has been literature on this, both from the Louisiana and Texas side. From Louisiana side, there was a report back in 1990, which looked at the highway embankments failures along Interstate 20 from Monroe to Talahua, and also from Lake Charles to Lafayette on Interstate 10. And so they found about 41% of the embankments had failed within 15 years of construction. And what was really interesting, contribution of this report, was looking at categorizing risk of failure based on index properties, liquid limit, clay content, and net SMEC type. That's manifested at the table below. The risk category is high, intermediate, low, and basically assigning a % chance of failure based on the range of plasticity indices and % clay. So the higher the clay concentration or clay size fraction and higher plasticity index represents a higher risk of failure. Thing missing from this table is the chance of failure is categorized, but at what time will that failure occur? Is it 5 years, 10 years, 15 years in the future? And after what event will it actually fail? And then in 2004, more research was performed to investigate rehabilitation methods in Louisiana, and this introduced the geotextile reinforcement method that is the standard repair for Louisiana. Moving over to Texas, this has also been investigated for many years. Stauffer and White back in the 1980s looked at a database of slope embankment failures along highways. Average age of failure was 20 years, and the local limits were generally above 50. And so they were developing correlations of slope ratio, slope angle with age of failure. More recently, the UT Arlington team, led by Anand Bhupala, has been looking at rehabilitation treatments from lime treatment, as well as propylene fibers and compost. So they have also been documenting failures as well in North Texas or Central Texas. And the rehabilitation has been ongoing as well with field implementation, more recently with DOT Texas DOT. So with regards to our Tran-SET project summary, again, we're coming back to the idea that this is an old problem, and what can we add to being able to understand when they will fail, these highway embankments, and what are the best techniques for rehabilitation. So this collaboration between LSU and UTA for slope stability embankments. So part of this work was looking at documented case histories of slope failures. So one of the first ones we looked at in Louisiana is in Itachi Lake. This is in the northwest corner near Shreveport and Alexandria, Louisiana. Right at the core of Interstate 49, if we zoom in to the dam, this road highway embankment also serves as a dam for the local community. And these embankments have seen multiple failures. That's indicated here by the yellow lines. 2 slope failures along the downstream face and 1 shallow failure along the upstream face. These had manifested several months or years before, and after Hurricane Harvey, they were exacerbated. So here's a closer look at the Itachi Lake. So here are some photos of the highway embankment failures. You can see the road has been closed in the lower left corner. Still, people use that road because they have to get to their homes. You can see the offset of the scarp from the roadway. You can see the subbase, and that represents about 3 feet of offset from the scarp. And while we were at the field, we noticed that there was extensive desiccation cracks all the way to about 18 inches. In another documented case study along Interstate 55 in Tangipahoa Parish, these embankments have failed consistently. There are 4 embankments. There's a railroad passing at this site along Interstate 55. There's 4 embankments, 1, 2, 3, 4. All 4 of them have failed within the past year. Sections 1, 2, and 3 were retrofitted or rehabilitated using deep soil mixing. And the research that's ongoing due to this transit project has led to, is leading to a test embankment at Section 4 on a newer technique for rehabilitation using not just geotextiles, but also active geotextiles that have a wicking capability. So in the figure in the top right also shows the scarp at that slope failure. A few sites in Texas. These are all located near Dallas, Texas, from Paris, Texas to Denison, Texas. Here we can see that the clay size fractions are quite high, above 40%, and high plasticities above up to 30. And so some of these sites have failed already and are being rehabilitating, and the UTA team is actually working with TxDOT on what methods to use for rehabilitation. And so this is also including field demonstration sites. So when it comes to analyzing these shallow failures, the photo on the top right shows that these are indeed shallow in nature, typically around 5 to 10 feet in thickness, typically about 20% of the height. Slope inclinations for these failures typically are about 2 to 1 to 3 to 1, and the embankment heights are around 20 feet to 40 feet. And when it comes to actually analyzing for a factor of safety or probability of failure, once you've identified the failure surface, there's a couple of things that we need to account for: pore water pressures, the shear strength at times of failure. So for the pore water pressures, typically what's been done is using the pore water pressure coefficient, RU. And this pore water pressure coefficient essentially uses the method of slices when we're performing slope stability analyses. It calculates the pore pressure based on the total stress of that slice. So pore pressure divided by normalized by the total stress. So if we come over here to a slice in the slope stability analysis, the program will calculate the total stress acting for the slice, and you prescribe an RU value, 0.4 to 0.6, back calculated from inverse analyses of failures, and you apply this value to your total stress to get the pore pressures. So this represents the current state of practice. What would be the next step, and what we're moving towards with this Tran-SET project, is actually modeling the current conditions in the embankment using climate data, meteorological data that's high quality from temperature, humidity, precipitation, and actually understanding what is the pore pressure in these slopes at the time of failure. For the shear strength, we know that these highway embankments are shrinking and swelling. And so when you compact that embankment, it has a peak strength. Over time, due to the shrink and swell process, that peak strength is reduced to a fully softened strength. So you have unsaturated compacted soil. The presence of cracks that we've seen applies shear stresses. That allows infiltration of water. That allows then swelling and expansion. And you have weathering, softening, and repeated cycles. And over repeated cycles, that leads to a critical state shear strength called the fully softened shear strength, represents as a drain strength. And that's where the bonds are lost due to the overconsolidation, and that edge to face interaction of the soil particles is lost. So as a result, you have a reduced shear strength. The figure on the right shows that peak shear strength that the embankment would see at time of construction. And we know that at some point, maybe 15 to 20 years to 25 years, this shear strength envelope is going to reduce to a normally consolidated, fully softened state, represented by no cohesion, but the friction angle stays the same between the freshly compacted and fully softened. The question, though, that remains, and what this Tran-SET project is moving towards, is how does this shear strength reach the fully softened state? Obviously, it's wetting and drying cycles. Typically, a laboratory test is focused on wetting and drying cycles from an extreme case. So you completely wet, completely desaturate, and you use those number of cycles to understand the strength loss. But what is the actual wetting, drying cycles in the field? It's not as extreme as complete saturation, complete dry. And so using field data and the numerical modeling, we're trying to quantify that wetting, drying cycles in the field so that when we start the laboratory testing, those wetting, drying cycles are accurately replicated. In lieu of measuring the shear strength, there's also correlations for the fully softened shear strength. This uses clay size fraction and liquid limit to determine the shear strength envelope we see here on the right. And this would be the yellow, orange, and gray lines. So there are correlations available to get to the fully softened shear strength. And what's not been done yet is calibrate or validate those correlations for Louisiana and Texas soils. So part of our work right now is to evaluate the shear strengths from Texas and Louisiana and verify that these correlations for clay size fractions of 20 to 50% and liquid limits from 0 to around 200% are applicable to Texas and Louisiana soils. And if they are, then they allow us to evaluate the fully softened strength of these highway embankments and allow us then to move towards understanding. So moving from stability analysis to the unsaturated conditions, once we have the shear strength, a key component to understanding what the pore pressure at the time of failure is understanding the transition from unsaturated embankments to the saturated embankments. So we are first quantifying the unsaturated properties, specifically the soil water retention curve for Texas and Louisiana soils. So here we have the Fredlin device, and we're taking samples from Texas, compacting them into the chamber. This is leading then to applying different matrix suctions to get and volumetric water contents to get the soil water retention curve. So here's 3 different soil water retention curves for Texas soils. And what we notice here from these 3 key considerations when developing the Van Gunington model for potential modeling is the alpha and M value, NN. M and N are interrelated, and alpha represents the capillary fringe, air entry volume. The key takeaway here is the N value is pretty constrained, about 0.5 to 0.7. N represents the steepness of the soil water retention curve. So that would represent how steep this portion of the curve actually is. Alpha represents the air entry value, and that's essentially when air bubbles start to form or occur in the soil matrix. And so conditions to the left of the air entry value represent the soil still acting under saturated conditions. And so if we look at the air entry value, we can then inverse that and multiply it by 10 to get to the matrix suction, and the average or the range of alpha values come about 150 to 380 or 350 kPa. What that represents is if your matrix suction is less than these values, you're still at a saturated hydraulic conductivity or near saturated hydraulic conductivity. And that's important when looking at what is the actual in situ pore pressures matrix suction in the soil. Is it going to be mostly saturated conditions or unsaturated behavior? And to get to whether we're going to be unsaturated or saturated, one of the key things that we're doing is actually incorporating the climatic events, extreme events. So here is a schematic of the drought severity index for the country. This was back in 2011. At that point, Louisiana was undergoing a severe drought, and the Midwest and Northeast of the U.S. were undergoing extensive snowfall and rainfall. And so what we saw was, starting from January 2011, there was extensive precipitation in the Midwest and Northeast, and we were under a drought condition in the South. And as that rainfall melted, it led to higher Mississippi River levels and higher drought conditions, essentially a combination of drought conditions in Louisiana and high precipitation water levels in Louisiana. So the effects of the drought in Texas and Louisiana, how does that actually how can that be incorporated in our slope stability models? So here's an example of data from the LSU Ag Center. We're incorporating precipitation, temperature, relative humidity, and solar radiation into our slope stability models to understand what is the pore pressures during a drought, before a rainfall event, after a rainfall event. One of the key areas that we want to focus in on is where the drought was occurring for Louisiana, and that's located in this region here, around a elapsed time of 600 days. And we can notice from the relative humidity being in Louisiana, we're typically above 80%. And once the drought hits, we can see that the humidity decreases to around 50%. What effect does that have on the highway embankment in terms of the suction profile? So we can incorporate these parameters using evapotranspiration, climate, soil, atmosphere, boundary conditions, and we can start visualizing what happens to the pore pressures. In this animation, this represents a highway embankment where the soil atmosphere boundary condition is applied just to the surface. We have a groundwater table several meters below the original grade, and we want to understand what is that water pressure matrix suction. So these contours represent matrix suction. Here on the legend, we see that already the matrix suction is between 20 to 15 kPa, so much lower than those air and tree values. So this period is during the drought for Louisiana. We want to see how the matrix suction is affected, how the drought affects the pore pressures in the embankment. So we'll start off at January 1st and slowly move over to March 1st. Okay. So during the drought event, we see just modifications to the matrix profile. They're typically pretty homogeneous because we're modeling this embankment as a homogeneous material. But for the most part, we're in a fine range of 10 to minus 20 kPa in terms of matrix suction. And then once we come out of the March 3rd or March 1st to 2011, Louisiana picks up the rainfall and the groundwater table will start to increase again. But for the most part, the embankment is unsaturated during this entire period. So as a comparison to, if you were to include climate-coupled modeling versus non-climate-coupled modeling, the figure on the bottom here shows if you had a non-coupled climate model. And what the non-coupled climate model will do is, just like a hydrostatic conditions for saturated, it will linearly interpolate the matrix suction linearly with depth. So if the water table is here at this depth, based on the thickness from the crest or the top of the embankment to the groundwater table, it will define the matrix suction based on per meter. So we can see here that this is minus 6 meters of matrix suction to minus 7, so that represents closer to negative 80 kPa matrix suction, which is drastically different from if you use a coupled model incorporating the evapotranspiration precipitation. The matrix suction profiles are much more uniform and closer to 0, just between minus 10 kPa matrix suction. So there's a markedly difference in the behaviors during just regular drought versus rainfall events based on whether you include climate versus non-coupled models. So with preliminary conclusions for this work, we understand that there's wetting and drying cycles leading to decreased shear strength and changes in hydraulic conductivity. That is then leading to greater pore water pressure during precipitation events, leading to potential failures. So the research directions are moving towards understanding the time-dependent behaviors in that drain shear strength and the soil water retention curve, and then taking that information, coupling it with slope stability analyses that incorporate extreme weather events to actually predict slope. And this would then help develop a framework for when a failure will occur due to an extreme event. And also we can start looking into rehabilitation based on field sites.